Welcome back to Biology 181. This is Dr. Patterson, and we are going to do a little lecture here on Chapter 4. Chapter 4 in chemobiology deals with carbon and the molecular diversity of life. Okay, so just a quick overview. Carbon. Carbon is really where we're starting. It's the backbone of life on our planet. Despite cells being composed of up to 95% water, the rest consists mostly of carbon-based compounds. And all of the macromolecules that we're going to tackle in Chapter 5 next week are going to really surround themselves or really be based off of this whole carbon concept. So it's important that we understand this so that the next chapter works as well. And the really neat thing about carbon is that it has this ability, unlike pretty much any other element that we deal with, to bond into and to form very, very large, complex, and very diverse molecules. So diverse as to be the difference between a sugar and a protein, or even a lipid and a protein, or a lipid and a sugar. So really, really, really diverse. We'll be looking at all of those, but like I said, let's start with carbon. So first definition, organic chemistry. Organic chemistry is the study of compounds that contain carbon. These compounds can be very, very simple molecules or very, very colossally complex ones. So I'm not a fan of the all and none version of statements, but when we talk about organic compounds, we absolutely can say that all organic compounds contain carbon. The vast majority of those also contain hydrogen. It's not an all statement. It's pretty close to an all statement for what we'll deal with here in class, but remember that organic compounds always contain carbon. So historically, we've had two concepts. We've had vitalism and mechanism. Vitalism was the idea that organic compounds came only from organisms. Okay? This theory, this vitalism theory, was disproven. Chemists were able to synthesize compounds without organic or without organisms being present. That has led us to mechanism. And mechanism is the view that all natural phenomena are governed by physical and chemical laws. So what we're looking at here is we're looking at an experiment by Stanley Miller. This experiment was performed in 1953, and Stanley Miller's question was this: can organic molecules form under conditions that we believe to simulate early Earth, the environment in early Earth? So Stanley Miller set up this closed system to mimic the conditions that he thought existed on early Earth. This is a prime example of systems biology, that term that we learned in Chapter 1. So let's just run through this quickly and let's see if this will help. So here we've got this flask of water. Sorry about that. This flask of water, and it's going to represent the primeval sea. What Stanley Miller did was he heated this water. He heated it so that some of it vaporized and moved in up through this tube into this second flask. Okay, this higher flask up here. This higher flask was designed to represent the atmosphere, and he used electrodes to discharge sparks into the atmosphere. The idea being that he was going to mimic lightning. We then get condensation. Okay, we're going to have that condensation come down. We've got this cooled water, because we have a condenser here with cooled water. This cooled water containing the organic molecules is going to come down. This was the sample that Miller used for chemical analysis. And the results were pretty impressive. So he was able to identify a variety of organic molecules that are common in organisms. Specifically, he found formaldehyde, hydrogen cyanide, and some more complex molecules that were very, very similar to amino acids and long chains of carbon and hydrogen, basically hydrocarbons. What Miller concluded was that, that organic molecules are a first step in organic life, and that in essence they could have been synthesized abiotically, so without the presence of life, without the presence of organisms. That was a pretty big deal. again, 1953. So prior to that, we didn't even think that this was even remotely possible. So one of the really cool things about carbon that we have to learn is that, I said it was very diverse. It can form very simple molecules or it can form very large, complex molecules. And the question then is, why? Why? What about the electron configuration to carbon allows it to do this? And it's really simple. Remember that your definition of electron configuration is just where are those electrons in the valence shell. Okay, so how that configures will determine what kinds of bonds can form, how many bonds can form, and with a valence of 4, carbon has the ability to enter into 4 covalent bonds with a variety of atoms. And that valence is really essential because carbon then can partner up with hydrogen, oxygen, nitrogen, and those in combination with carbon are really the building code. They're the building blocks that are going to govern what living molecules look like. So visually, we can have a very simple short chain, 2 carbons with some hydrogen around it. This is ethane. We can have a little bit longer chain or a longer chain. These both over here have single bonds. Now I've started to add in double bonds with 1 butene and 2 butene. So we've got this, they can be long, they can have length, we can have double bonds. We can have branching. So we can have this right here. Okay, 3 carbons here, 1 carbon up. So this is a 4 carbon molecule, as is this, but they're very differently shaped. Or we can even have rings. So here again, I have 1, 2, 3, 4, 5, 6 carbons, but they're all bound together with single bonds. Over here, I still have 6 carbons, but I have less hydrogen because I have some double bonds forming into that ring. So carbon is very, very versatile, and it's that versatility that allows it to form so many different shapes. I said a word a little bit ago, and that was hydrocarbons. Hydrocarbons, by definition, are organic molecules, so they contain carbon. But the thing about hydrocarbons are that they only contain carbon and hydrogen, nothing else. So if you have a molecule with just carbon and hydrogen, you're talking about a hydrocarbon. Many larger molecules, many of the organic molecules, are going to have hydrocarbon regions or portions or components. So like the fats will have regions that are hydrocarbons. And the neat thing about hydrocarbons is that they can undergo chemical reactions and release large amounts of energy very easily. Remember a couple slides back when I said I've got this 4 carbon and this 4 carbon and they look very differently. So I need to talk about something called isomers. And isomers are compounds that have the same molecular formula, but they have different structures. And because they have different structures, they have different properties. So we can have, and there's a visual on the next slide. So we can have a structural isomer, we can have a geometric isomer, and we can have an enantiomer. So structural isomers are going to have different arrangements to their covalent bonds. Okay, so this is a structural isomer. This chain versus the branching. Structural isomers. I'm going to go back a slide just so you can read the words. Geometric isomers have the same covalent arrangements, so the same bond arrangements, but they're going to differ spatially. Okay, the space between is going to be different. So what we've got here in these geometric isomers is, here's my double bond, and I have these 2 unknown, these 2 branching groups, the 2 X's, are on the same side of that double bond. That's called a cis isomer. Or I can have a different version of geometric isomer called a trans isomer. In this case, those X groups are on opposite sides of the double bond. You have to draw a line across the double bond to connect them, whereas over here I don't have to cross the double bond at all. Backing up one more time, enantiomers are isomers that mirror each other. So it's like your left and your right hand. They're mirror images of one another. And here's an example of an L enantiomer and a D isomer enantiomer. Enantiomers are really important to the pharmaceutical industry because they are, like I said, mirror images of one another, and two enantiomers can have very, very different effects. So, same elements in the same ratio, put together very, very close structurally, except that they are the mirror image of one another. It's this difference in the enantiomers that give little variations to molecules. So here's an example. Okay, so this is ibuprofen. It's used for pain and inflammation. It's an NSAID, or non-steroidal anti-inflammatory. This version, the S-ibuprofen version, is effective. It binds, it works, it just does the job we expect the NSAID to do. If the pharmaceutical industry produces the R version, the ineffective enantiomer, the mirror image of S, which they have done, by the way, that's how we get to know these things, it doesn't work. Same thing when we talk about albuterol for the treatment of asthma. The R-albuterol works, the S-albuterol does not. It has little to no effect at all. So it's just this mirror imaging that can make all the difference. Okay, so we need to start talking a little bit about some functional groups. So one of the things that I do in this course is I pick some big functional group categories that are very, very common, 7 of them I believe, that are very, very common to biology. And I ask you to know some things about those 7, because those are the 7 that are going to pop up again in 182. They'll pop up again later this semester in 181. They'll definitely pop up when you start talking about different processes in 201 and 202. Okay, so functional groups. Functional groups are a branch, or not even a branch, but something that's bonded to the carbon skeleton, okay, and it has specific characteristics to it. So here we go. There's your full definition, okay, and then it's the number and the arrangement, how they're put together, that give us our functional group. So in this case, I have this is the same, this is the same, this is the same. And then look at this. In testosterone, I have a 1 carbon and 3 hydrogen coming off this ring. I have a single double bond within the carbon ring, and then I have a double bonded oxygen over here. In estradiol, which is a precursor to estrogen, it looks different. These are the same, but now I've got these 3 double bonds here. I don't have that CH3 group. I don't have a double bonded to the oxygen, but what I do have is an OH. I have a hydroxyl group hanging off the edge here. So similar but different, and it's these functional groups that cause these molecules to act differently, to be bound differently in the body, and to have very different responses. Okay, so there are 7 functional groups I want you to look at. The end of this PowerPoint slide presentation has all the stuff you need to know, but there are 7 groups. The hydroxyl group, I'm going to say them so you can pronounce them: carbonyl group, carboxyl group, amino group, sulfhydryl group, phosphate group, and methyl group. All right, but before we get to those, I need us to talk about ATP. ATP is the energy currency for cells. So a cell needs to do work, it needs ATP. The same way as you want to buy a new download song, you need money. Okay? Cells need ATP to accomplish work. It is their energy. You don't eat ATP, you eat other macromolecules that then are able to be broken down, and the parts that made them up are able to be rearranged, and you generate ATP. Specifically, we use glucose a lot for this, but we can use proteins, so carbohydrates, we can use proteins, we can use lipids, any of those guys. All right, ATP is a single phosphate molecule. Okay, 1 phosphate molecule. It's adenosine triphosphate, so ATP stands for adenosine triphosphate. And what I have here is I have a 5-carbon sugar called ribose. Okay, I have adenine. I have a group adenine, and I have 3 phosphate groups. Okay. All right, and what happens here is we break this bond between the phosphates. We want to cleave off the furthest out phosphate, and when we do that, it releases energy. So I go from adenosine triphosphate, I've cut off one of these phosphates. I do this with water, by the way, and now I have ADP, or adenosine diphosphate. We're going to come back and talk about this a bunch in chapter 8. I think it's 8. It's the energy and enzymes chapter. But I just wanted to introduce it to you. Okay, so as I promised, functional groups. And I just have, I think, 3 slides. So this is your supplemental guide. This is in the textbooks, pretty much every Campbell biology textbook that's ever existed. I want you to be able to, this should say 7. Cross that out and write 7. List the 7 functional groups in the handout. Be able to draw that structural formula for each. I want you to name the class of compounds associated with this. So we're going to go through this, a couple of these together. And then you need to match the properties with the chemical group. So, for instance, that's kind of small. I wonder if I can blow that up. I bet I can't in the recording program. I bet it doesn't let me. No. Okay, so over here you've got on the far left, sorry, my cursor's on the right. On the far left, you have the hydroxyl group. Its structure is a single bond attached to an OH. Okay, then there's a bunch of names of compounds here. Okay, so alkaloids, their specific names usually end in "all." I'm sorry, that says alcohols, not alkaloids, my bad. So alcohols, their specific names typically end in "all." Ethanol, glycerol, okay? This is an example of, where'd my cursor go? This is an example of ethanol, okay? And these are the properties. So you want to know the group, you want to recognize it or be able to draw this part in purple. You want to know that these are the alcohols. This example is just to help you see it, and then you want to know some of the properties. So you've got 7 of those. So you've got hydroxyl group, the carbonyl group, the carboxyl group, the amino group. This will be really important when we start talking about amino acids. The sulfhydryl group. This will be really, really important when we talk about cellular respiration. Phosphates are important to ATP and other energy resources. And then the methyl groups. We'll talk about methylating DNA and what happens to DNA when we add a methyl group to it. So like I said, these images are also in your textbook, or you can find them online. But I want you to know those key pieces to that. I'm going to end this video and get it uploaded. So have email me with questions. We'll see what we can do.